Swayam Prabha. Digital India. Educated India.
Hello all, welcome to the first lecture of this course, Flight Dynamics and Performance, MATLAB and Simulink Approach. I am Dr. Prabjeet Singh, PhD in Aerospace Engineering from IIT Kanpur with a specialization in flight mechanics and control. Now in this course, we'll be dealing about basics of flight mechanics. Now there are multiple courses available in an online platform. Now how this course is different from other available online courses? Well, we'll be doing the simulation with the equations that we'll be using and deriving during the tenure of this course, and we'll be simulating in MATLAB and Simulink. Now, you may not be as efficient in Simulink and MATLAB, but we will be dealing with the basics of coding. So, by the end of this 20 hours course, you will be well versed with flight mechanics as well as simulation and coding. Now, let us quickly deep dive into the syllabus of the content that I will be covering in this 20 hours course. Now, we will talk about basics of flight mechanics, types of airfoils and the nomenclature that we will be discussing in today's class. Later, we will be discussing about aerodynamics of the airplane, their coefficients, drag types, lift on the finite and infinite wings, then modeling of standard atmosphere in MATLAB. Then we'll be beginning with the equations of motion, that is steady level flight performance, thrust required, velocity relationships, followed by thrust available and maximum velocity estimation. Then we'll talk about power required for level flight, power available, what is the maximum velocity with which the aircraft can actually fly, and the climb performance analysis, rate of climb, climb angle, along with the photograph construction in MATLAB, followed by gliding flight and ceiling estimation. Then we'll talk about aircraft range, the horizontal distance the aircraft can travel, as well as the endurance, that is the amount of time spent in the air, followed by the accelerated flight performance, modeling level turn performance, minimum turn radius and maximum turn rate. And then we'll talk about pull up and pull down maneuvers, constructing VN diagram, and finally takeoff and landing performance analysis. Now let us quickly before that, these are the textbooks that I will be referring to. That is Introduction to Flight by J.D. Anderson, Aircraft Performance and Design by J.D. Anderson again. Then a very good book written by IIT Kanpur Professor Tiwari. Textbook name is Atmospheric and Space Flight Dynamics. And finally, The Mechanics of Flight by Warren F. Phillips by John Wiley and Sons publication. Now let us quickly go to our first topic. Now, before I begin the first lecture, in the first lecture, I always talk to students and ask about the basic questions about an aircraft, like how does an aircraft fly? Now, we'll be basically dealing with the fixed wing aircraft. Now, what are the forces that are actually acting on the aircraft? All right. And followed by that, what is the altitude at which the aircraft fly? Okay. Now, the question that I ask students generally is, what are the various forces that are acting on an aircraft? For example, most of you or few of you must have flown in an aircraft, for example, in Boeing 737 or Airbus A320. So, what do you think is the mass of such aircraft? Right? So, when I ask this question to students, so most of them will answer about 5,000 kgs. Sir, 10,000 kgs, and then maximum around 20,000, 25,000 kgs. But let me tell you, my dear friends, the Boeing A737, let me just write down here. Boeing 737, the mass of such an aircraft is approximately around 80,000 kilograms. Similarly, Airbus A320, its mass is again around 75,000 kilograms. Now what about the biggest passenger aircraft in the world? Now which is the biggest passenger aircraft in the world? Yes, you guessed it right, Airbus 380. Now when I ask students the mass of such a huge aircraft in the world, then their answer would be around maybe 1 lakh kgs or 1,20,000 kgs, 1,50,000 kgs. But the mass is around 5,75,000 kg. Alright. The idea behind telling you these numbers is that I want you to appreciate the amount of the upward force or the lift, which I'll be talking about it in depth in the later classes. The amount of upward force required for these heavy bodies to lift in the air is colossal. It's very huge. Alright. And since we are talking about fixed wing aircraft, most of this upward force is created by, yes, wing itself. Alright. Now let us focus on this wings geometry, how the aircraft is able to produce that much amount of lift and then propel into the air. Alright. Okay. Let me draw this wing over here, which is a 3D wing, and if you draw a cut section of this wing over here as shown here, it will look something like this shape. Alright, so these are nothing but streamlines flow. Now this is a cut section of a wing. And this shape is generally called as airfoil shape. Okay. The shape is known as airfoil shape. Now what happens here is, to lift such heavy bodies into the air, we need a higher force at the bottom and the lower force at the top. Alright. So here we have high pressure at the bottom surface of the airfoil, and here in the top we have low pressure at the top surface of the airfoil. Now suddenly we are talking about the pressure differences between the lower and the upper surface of the airfoil. Now how does an aircraft fly? It basically depends upon two principles. So one of the principle is, yes, it is Bernoulli's principle. Alright. So let me write down Bernoulli's principle here. So it simply states that for incompressible steady and frictionless flow of a fluid we have this equation P plus half rho V square plus rho VH equals to constant. I am sure you must have heard about this equation before, where P is nothing but static pressure, rho is density, V is of course the velocity, G is the gravitational constant, and H is of course the height. Alright, height above the reference level. Now let us assume that aircraft is flying at a constant altitude. So that means your height is constant. Alright. So now we can further reduce this equation to P plus half rho V square equals to constant. Alright. Now the bottom line of this equation is that P is actually inversely proportional to the velocity. So if we have high pressure, then obviously we'll be having low velocity. Alright. And inverse is also true. Low pressure will lead to high velocity. Now please focus here on the figure. So in the bottom surface we have high pressure. So that means here we'll be having a low velocity. And in the top we'll have low pressure and high velocity. Also note that the upper surface of the curve, the airfoil is actually curved and the bottom is actually a little bit flat. So this is how we actually obtain the pressure difference between the lower surface and the higher top surface. The idea behind is to create an upward force which is created by this difference of pressure. So always remember, because of the pressure difference. Because of the pressure difference, we obtain this result. Now, to obtain this pressure difference, obviously the aircraft should have some certain velocity, right? Now, when I ask students about this question related to commercial aircrafts, so how much velocity do we need for the aircraft to actually start obtaining this pressure difference? In other words, how much velocity is required for takeoff? Alright. Now, consider 737 or any commercial aircraft. So, when I ask this question, so they usually tell about 100 kilometers per hour. Alright, that is somewhat okay, but it generally requires about 200 kilometers or 250, even 250 kilometers per hour to attain that much velocity, and then pressure difference starts creating. Alright. Now, the second principle on which it depends, you must have guessed by right now. And the second principle on which it depends is, yes, it is Newton's third law. Alright. So let me write down here, the second principle is Newton's third law. It simply states for every action, there is an equal and opposite reaction. Alright. Now, how do we get this force or forward force? We get it from the engine. So, engines are able to produce that much amount of forward force or thrust which will propel the aircraft to certain velocity, say 200 kilometers per hour. And then the Bernoulli principle comes into picture and the pressure difference is created, and finally the aircraft takes off. Alright. So next time if somebody asks you how does an aircraft fly, simply mention it flies because of the combination of these two principles. Right. The first is the Bernoulli's principle and the second is, yes, Newton's third law. So these two work together for the aircraft to successfully take off and fly. Alright. Another perspective is the momentum perspective. See, the air is actually pushing the aircraft downward, right? And then in turns it pushes the aircraft upward. Alright, so this explains in terms of momentum perspective as well. The upward force, I am calling here it as a lift as of now, but we will be defining that lift very soon. Alright, so this was about the lift generation. Now, the next question that I ask to students is, what are the types of forces that are actually acting on an aircraft? Alright, so let me just draw the free body diagram again. Forces acting on an aircraft. So consider this point, assume it is the forces which are acting on this point. One is of course the weight of the aircraft. Second is the thrust, that is because of the engines. Upward force, that is the lift. And there is one more force, it's nothing but drag. Alright, now we can actually classify these forces. So the first classification is of course the gravitational forces. This is denoted by weight W. Second is propulsive forces. Denoted by thrust. What about the third one? The third one we have lift and drag. So these are classified under aerodynamic forces. Okay, lift and drag will be coming then the next class, or what is the definition of the lift and drag. So now that we know what are the types of forces that are actually acting on an aircraft, one is the gravitational force, second is the propulsive force, and next is the aerodynamic force. After this, I asked students what is the altitude at which the aircraft is actually flying. Okay. Now, what is the altitude at which the aircraft actually flies? Now, they simply mention about maybe 20 kilometers, 30 kilometers, or 40 kilometers. Alright, but few of them answer the correct answer also. So it depends upon the aircraft type. Alright, so generally speaking, the commercial aircraft they fly at about 10 to 12 kilometers. Alright, so let me just write down with the aircraft classification at which it flies. So it again depends upon first of all the aircraft type. The second is of course the mission profile. What is the mission profile of those aircraft? Alright, so let me just write down here. The first classification is light aircrafts. So I denote aircraft as A by C. Okay, so you can consider, for example, Cessna aircraft. It flies at around 1000 to 5000 feet. We denote it generally by feet as well. It is approximately 1.5 kilometers. And the reason is visual navigation. Alright, or low speeds of such aircraft. Okay, this was the first light aircraft type. Second, let us talk about commercial jetliners. Okay, so as I said, it flies at around 35,000 to 42,000 feet. Okay, which again is approximately 10 to 12 kilometers. The reason is fuel efficiency, and of course if you fly above the weather, it becomes easier to actually navigate and comfortable for the passengers as well. Alright. Another classification is of course the fighter jets. Which flies at usually around 50,000 feet to 60,000 feet. It's approximately around 18 kilometers. And the reason they fly at this altitude is because of the high speed intercepts. They need to intercept the incoming aircrafts. So the reason is high speed intercept and the radar coverage. Another classification is high altitude unmanned aerial vehicles. I am writing it as UAVs, high altitude unmanned aerial vehicles. It can go beyond 60,000 feet as well and above. And the reason they fly at this region is obviously because of the surveillance. Another classification is, of course, the helicopters. Their range is generally around 10 to 12,000 feet, approximately 3 kilometers. The reason is hovering. And since we know they need higher density of the air for the helicopters to actually start creating lift or the upward force. That is why their altitude is generally not as high as when compared with the other types of aircraft. Alright. So I think with this is clear about the type of classifications of the aircraft. Now let us quickly begin and the nomenclature of the airfoil. Airfoil nomenclature. Let us begin with airfoil nomenclature. So prior to 1930s, so there was no systematic approach in creating or assigning a proper nomenclature to the airfoil. So then came the contribution of NACA, that is National Advisory Committee for Aeronautics. Let me just write down the acronym for this that you should know. NACA. National Advisory Committee for Aeronautics. So they simply define certain rules if you are designing any type of airfoils. So they adopted a rational approach, and then let me just draw the airfoil figure over here. So this front portion is generally called as the leading edge. The end portion is called as trailing edge. This is nothing but chord denoted by C. This shape that you are seeing over here is called as mean camber line. Alright, and this is called as the thickness of such airfoil. Okay. And the distance between this mean camber line is called as camber, simply the camber. So now we have defined certain parameters: leading edge, trailing edge, chord line, thickness, and mean camber line. So let me write down the definitions of each of these terms so that we are aware about what we are actually dealing with. So let me write first the mean camber line. So the major design feature of an airfoil, this is major design feature . of an airfoil which is the locus of points halfway between the upper and lower surfaces. As measured perpendicular to mean camber line itself. Okay, so this defines the shape of the airfoil. So look at this figure carefully. So this is actually defining the shape of the airfoil, which is nothing but locus of points halfway between the upper and the lower surface of any airfoil. Alright, so this was about mean camber line. Let us quickly move to the next definition, that is the simplest of all, leading edge and trailing edge. So the most forward and rearward points of mean camber line are the leading edge and trailing edge. Respectively. Alright. See here, the most forward point and the rearward point is called as the leading edge and trailing edge. Alright. So let us move to the next definition, that is the chord line. It is again one of the simplest definitions. The straight line connecting the leading edge and trailing edge is the chord line, which is usually denoted by small letter c. Okay, that straight line, which is this dotted line that you are seeing over here, which is connecting the leading edge and trailing edge, is known as the chord line. Now finally, what is the camber? So from the figure itself, you can make it out that the camber is the maximum distance between the mean camber line and the chord line when measured perpendicular to the chord line itself. Alright. So I am expecting you to write notes with me. Please take a pen and paper and write notes along with me. So this is the maximum distance between the mean camber line and the chord line when measured perpendicular to the chord line. Alright, so now we have defined few definitions over here. So NACA came up with a few series of airfoils. One is 4-digit series, 5-digit series and 6-digit series. So let me write down NACA 4-digit series first. Now we want to know if there are 4-digit series, what do you mean by the first digit, second digit, third and fourth digit? Alright, so consider 4-digit series, for example, 2412 airfoil. Okay, so what do you understand by this nomenclature or the series, that is 2412? Alright, that is what we are after. So the first digit gives maximum camber in percentage of chord. So let me write here by symbol percentage of chord. Second digit gives the location of maximum camber in tenths of chord. When measured from the leading edge. Okay, do not forget this, when measured from the leading edge. I am writing here leading edges L dot E dot. And the third and fourth digits give maximum thickness. In percentage of chord. Okay, now coming to 2412. The 2412 defines what? The first digit is giving maximum camber in percentage of chord. So that means maximum camber of the first digit is 2. So that is 2% of chord, that is 0.02 C, which is actually located at this distance. If you find it is at 0.2 of chord, which is actually located at some 0.2 distance from here, from the leading edge. Alright. So now in this case, it is located at 0.4 C from leading edge. And finally, the last two digits are actually giving the maximum thickness. So here we have maximum thickness is 0.12 C of chord. Alright. Okay. So now before I move to the next series of airfoil, I just like to mention that the airfoil that I have drawn here is actually a cambered airfoil. Alright. In cambered airfoil, obviously there will be a mean camber line. Now there is another type of airfoil, that is symmetrical airfoil. Let me just draw a diagram over here. Okay. So now if you notice here, this chord line here itself, we do not have any camber. The chord line is exactly between the upper and the top surface of the airfoil. Alright. So this is known as symmetrical airfoil. Now for a symmetrical airfoil designation, if there is no camber, alright, then obviously there will be no location of camber as well. Now what will be the series designation? Say for example 4-digit series. Yes, you are right. So the first 2-digit series will always be 0. And next will be defining, third and fourth will be defining, for example, 12% of or maximum thickness of the chord. So whenever you see these first 2 digits of any series of the airfoil, then the first thing that should come to your mind is that this is a symmetric airfoil. Okay. Right. So now let us move to the next NACA 5-digit series. Now in the middle 1930s, the researchers found that the lift is actually increasing when the location of the maximum camber was found near the leading edge. Okay. Now let me just write down here itself. They found that researchers noted that the lift or the upward force, that lift increases when the location of maximum camber is near the leading edge. So that's why they came up with the 5-digit series airfoil. So here we'll again talk about the first digit, which is when multiplied by three by 2, this gives us design lift coefficient. Now what is design lift coefficient? This is the coefficient, lift coefficient at angle of attack for normal level flight. And which is usually around 2 to 3 degrees. Alright. Now I have taken the name of angle of attack. So I need to explain what exactly is this. Consider an airfoil. Now this is the chord line. And this, for example, is the direction of airflow. Alright, and this is the chord line. And the angle which is defined between the chord line and the direction of airflow, or the velocity you can mention over here, that is nothing but the angle of attack. Alright, and this we denote it by alpha. Now let me first write the definition of angle of attack. The angle between the chord of the airfoil and direction of airflow. Or we call it as relative wind. Okay, it is denoted by alpha. Alright, so here angle of attack is the angle between the chord lines as well as the direction of the airflow. Alright, now while defining the first digit, I mentioned here which first digit you have to multiply it by 3 by 2. That will give us the design lift coefficient. Lift coefficient at the angle of attack for normal level flight. So generally for level flights, the angle of attack is usually around 2 or 3 degrees. Alright. Now this was about the design lift coefficient as well as the angle of attack. Now let us talk about the second and third digit. So this when multiplied by 1/2, so this gives the location of maximum camber relative to leading edge in percentage of chord. Okay, so the first digit was multiplied by 3 by 2, and for the second and third digit is multiplied by 1/2. It gives the location of maximum camber relative to the leading edge in percentage of chord, which is again the similar point for the 4-digit series as well. Alright, only the thing is it is multiplied by 1/2. Alright, and the last two digits that will be same. So the last two digits give maximum thickness in percentage of chord. Alright. Now consider NACA 23012 airfoil. Now as per the designation, the first digit when multiplied by 3 by 2, it is giving lift coefficient at angle of attack for normal level flight by at around 2 or 3 degrees. So let me write here again, NACA 23012. Alright. So the first digit is 2. You have to multiply by 3 by 2, which gives 3. So this will be giving us the design lift coefficient of 0.3. Alright, so note there is no percentage of chord. This is the design lift coefficient of 0.3. Next is the location of maximum camber. Which is at 30, next to this is 30 into 1 by 2. This will give 15. But that means 15% of chord, 0.15 C from the leading edge, and finally the maximum thickness of 12% of chord. You can mention here 0.12 C. So now we are done with the two series of airfoil, that is 4-digit series and then 5-digit series. We know exactly what each digit is actually representing. Now next comes the NACA 6-digit series. Now here during late 1930s, the NACA developed a series of airfoils designed to encourage laminar flow. Alright, the laminar flow is nothing but the smooth streamlines. And 6 series airfoil emerged. Alright, see, it's all started with the NACA 4-digit series airfoil during 1930s. Now we know what each digit is actually representing, and later on NACA developed NACA 5-digit series airfoil. The purpose was, the researchers noted that the lift is actually increasing when the location of maximum camber is actually near the leading edge. Hence the development of the 5-digit series airfoil. And further, in late 1930s, what happened is that NACA developed series of airfoils which is designed to encourage laminar flow, and 6-digit series airfoil emerged. Alright. So let me denote here, let me just first of all write the 6-digit series airfoil 64-212. Yes, the 6-digit series is actually denoted with a dash in between. Alright, so do not get confused. So let me just write here this number 1, the 6 series airfoil. 6 defines 6-digit series airfoil. Which is relatively easily identified. Okay. Now the second digit is, here we'll be having a new term, that is location of minimum pressure. In tenths of chord. I hope you are making notes along with me. The location of minimum pressure in tenths of chord behind the leading edge. Third digit gives again same design lift coefficient in tenths. Alright, not in chord. Please remember, this is the design lift coefficient. It is a unitless quantity. Okay. And the last 2 digits let me write from here. The last 2 digits they give maximum thickness in percentage of chord. Alright, that always remains same. Last 2 digits always define the maximum thickness in percentage of chord. Now let me write here again the series name, NACA 64-212. So here 6 is the series airfoil. With minimum pressure point at 0.4 C from the leading edge. Design lift coefficient is 0.2. Six series airfoil, the minimum pressure at point C from the leading edge. The design lift coefficient is 0.2 and the maximum thickness is 12% of chord. C. Alright. So now if you have 4-digit series, 5-digit series and 6-digit series airfoil, you can easily identify this nomenclature, what exactly it is actually meaning. So the first digit for the 6 digit is 6 series airfoil and the second is at the minimum pressure at 0.4 C from the leading edge. The design lift coefficient is 0.2 and the maximum thickness is 12% of chord. Alright. Now apart from these airfoils, now there are other types of airfoils as well. See, please note that these airfoils have been existing for the last 60, 70, 80 years and so on. Alright, and these airfoils are still in use. Okay. So these airfoils are still in use. If you see the wings design carefully, then you can actually see that these airfoils are actually employed in the real aircraft. Alright, and I was talking about the cambered airfoil. The cambered airfoils we generally employ at the wings section, and another type of airfoil was the symmetric airfoil. Symmetric airfoils are employed at the tail section of the aircraft. See, the purpose of the tail is not to create lift, alright, the upward force. The purpose of the tail is to create a movement, alright, that is the whole point. So these airfoils have been existing for the past 70, 80 years, alright, and this will continue to exist. And with the new advent of the unmanned aerial vehicles, that new series type of airfoil have also emerged. Okay, I would like you to explore these type of airfoils as well. So let me write down few types of airfoils which are currently in use. For example, in current UAVs, unmanned aerial vehicles, the first series or the name of the series of the airfoil is Simulink airfoil. Second is the Airbus series, airfoil, and the third is also Clark airfoil. Just write down again. Clark airfoil. And you are also encouraged to use Airfoil Tools website. Here you will be seeing different classifications of airfoils and explore about Simulink airfoils, Airbus airfoils, Clark's airfoils. What is the series designation of these airfoils? How do you recognize these airfoils? That will be more than sufficient for your basic understanding about the different types of airfoils. And also explore Airfoil Tools website, where you will be seeing different types of plots. So these plots we will be discussing in our coming classes as well. Alright. Now this was about brief understanding of the question that I generally ask during the first class, that how does an aircraft fly? Alright, what is the altitude at which the aircraft flies? What are the different forces that are acting on an aircraft? What are the two principles that it is actually depending upon? Alright, and what is the series designation of the airfoil? How did we come up with different types of series configurations? NACA 4-digit series, and NACA 5-digit, and NACA 6-digit. And this, as I said, has been existing for the past 70-80 years. And I also said you to explore about different type of airfoil, that is Simulink airfoils, Airbus, Clark airfoil. Alright. So in the next lecture, we will be beginning with a little bit about history of the aircraft. Alright. So that will be actually crucial in the coming classes, that how it all began. And then we'll be beginning with the actual content of this course. Alright. So let me just wrap it up at what actually we discussed in the first lecture of this course. So the first lecture covered about basic topics, that how does an aircraft fly, what is the altitude at which the aircraft is flying. Alright, so these are the basic questions that every aerospace engineer or any engineer should be able to answer if you are interested in aerodynamics or the flight mechanics of aircraft. Alright, and what are the different types of forces that are acting on the aircraft? There are three types of forces. One is the gravitational force, another is the propulsive force, and the last one is the aerodynamic force. So we'll talk about aerodynamic force in depth in the next class. So how this aerodynamic force is created, what are the sources behind this aerodynamic force, that along with little bit of history of the aircraft, that we'll be discussing in the next class. Alright. And one more thing, we discussed how the lift is actually created. The lift is created because of the wings, right? And the wings, if you have a cut section of the wing, that is nothing but the shape of the airfoil. And we have seen that it's a higher pressure at the bottom surface of the airfoil and the lower pressure at the top surface of the airfoil. That is how our main motive is. See, we want the aircraft weight which is having around 1 lakh, for example, kgs of the aircraft. Alright, so we need an upward force. So that upward force is created by creating a pressure difference between the lower and the upper surface of the airfoil. Alright, so we have higher pressure at the bottom and the lower pressure at the top. Please remember that these are the basics, and pressure is obviously inversely proportional to velocity. If we have higher pressure at the bottom, then there is a lower velocity at the bottom. So wings are designed in such a way that we finally get this pressure difference. Alright. Now what is the cut section of a wing? That is nothing but the airfoil. Alright. And this airfoil's development has been coming into picture since 1930. And we discussed in this lecture that there are 4-digit series airfoil, 5-digit series airfoil, and 6-digit series airfoil. Now, what does these digits represents that we have seen at length in this lecture? Alright. So now we will be having complete notes of this lecture of this 20 hours course. Please take a pen and paper and write down with me. Alright. In that way, you'll be understanding better. And in the coming classes, we'll be also adding the simulation as well. Alright. So let us meet in the next class. Thank you.